Hello everyone, I'm Geonsun Lee from Korea University, and I'll be presenting our work, a user study on view sharing techniques for one-to-many mixed reality collaborations. The area of mixed reality collaboration is gaining interest with the development of virtual reality and augmented reality technologies. While previous works mostly focused on one-to-one collaborations, practical uses of MR collaboration includes one-to-many user collaborations. View sharing of multiple users should be taken into consideration for real-world scenarios. To this end, we created an MR collaboration scenario where one VR remote expert instructs multiple AR local users. Our work focuses on comparing which view sharing technique is the most effective in instructing local users in the remote expert's perspective. In our study, the VR remote expert is wearing an HTC Vive HMD, and the AR local users are wearing Microsoft HoloLens with a 360 camera mounted on top of it. In our scenario, the remote expert instructs two local users to perform a task. The task is to direct the local user's actions to search for TANs and assemble them to a certain target configuration. For the workspace setup, a room is separated with a partition in the middle. One side being the VR remote expert's workspace, as shown in the figure on the left, while the other side is the AR local user's workspace, as shown in the right. In the local user's workspace, there are search tables and an assembly table. The search tables consist of 6 tables surrounding the local users, where TANs are scattered around, whereas the assembly table is a separate table in the middle for assembling the TANs. In our work, we compare 3 common view sharing techniques that are used in one-to-one MR collaboration. We modified them to fit our one-to-many collaboration scenario. The 3 techniques are named 2D video, 360 video, and 3D model. Let's take a look at them one by one. The first technique is 2D video. In this technique, the live video stream from the local user's HoloLens camera is shared with the expert, and the video frame is fixed to the VR HMD's screen. To distinguish between the user's views, the outline of the video frame is color-coded to either green or red. Distinct features are switching between the 2 local users with a fade-in fade-out effect to minimize the remote expert's thickness, and sharing remote expert's line pointer with the local users. The second technique, 360 video, utilizes the 360 camera mounted on the local user's HoloLens. Here, the live panorama video stream captured from the local user's 360 camera is shared with the expert. Here, we implemented counter-rotation to make sure the remote expert's view is independent of the local user's view. The view direction of the local user is depicted with a color-coded frame. This technique provides the remote expert with features as following. The transition effects and pointer sharing is also implemented as done in the 2D video technique. And additionally, the remote expert can view the local user's workspace independently of the local user's viewing direction. The last but not least is the 3D model technique. This technique pre-reconstructs the local user's workspace as shown in the figure below, and displays a live video billboard attached to the front of the user's virtual avatar. It goes without saying that all avatars' movements are synchronized with the local users. 3D model enables the remote expert to freely walk through the reconstructed space in VR. The remote expert's position and pointing line are simultaneously shared to both local users in this case. With the 3 view sharing techniques, we first conducted a pilot test to identify the weaknesses of each view sharing techniques and improve them. In this pilot test, 2 actors were employed as local users to minimize the performance differences, and 8 volunteers were recruited as the remote expert. Participants freely instructed between local users to search and assemble TANs with the 3 view sharing techniques. Collecting the feedback for each technique, we were able to modify and improve each of them. After trying out 2D video, there were comments such as, the view being full screen is unnecessarily big and it is hard to perceive it at a glance. We thus disabled the full screen mode, which resulted in the video having a black background. Next, in 360 video, participants complained that the image distortion created by the panoramic video makes it hard to identify TANs that are relatively far. To address this issue, we added a zoom in, zoom out function. There are also some feedback with the 3D model technique. As the current implementation uses a billboard, participants pointed out that the live video is only visible from a certain angle, which is especially inconvenient when instructing multiple users. A function is added so that the remote expert can switch between video billboard and a video projector. The latter is implemented with projective texture mapping. Furthermore, some participants stated that the pre-reconstructed 3D scene does not show the change made in the real workspace. Additional implementation enabled users to freeze the video frame in order to save the changes they have made to the static virtual workspace. In the main experiment, we wanted to identify which of the view sharing techniques is the best for the remote expert in a one-to-many MR collaboration scenario. 17 subjects participated as the remote expert, and this time a target configuration is rendered in the subject's VR screen. The goal of the task is to instruct the local users either verbally or with line pointing, and correctly search and assemble TANs. Subjects were given a training session before trying out each view sharing technique. Seen below is an example of a target configuration that the subject is aiming for, and the initial placement of TANs that the subject should replace or add TANs to. We assumed 2 common one-to-many collaboration scenarios in the real world for our main experiment. Scenario 1 independent task has each local user involved in both search and assemble procedures. Each local user can only access to 3 search tables, which is either the right or the left side of the room, that are assigned to him or her, while they both can use the assembly table in the middle. As for Scenario 2 divided tasks, each local user is dedicated to a certain role, either search or assembly. The user in charge of search can access to all 6 search tables, whereas the one in charge of assembly is fixed to the assembly table. Now let me present the results of the experiment. First, we analyzed the objective performance measures, search and assembly times for each scenario. For search time, 3D model was significantly shorter for both scenario 1 and 2. This can be explained by the high DOF of 3D model, allowing experts freedom of movement. For assembly time, 2D video was the shortest in scenario 1, since the remote expert's fixed view helped subjects to focus on the assembly procedure. However, in scenario 2, there were no significant differences observed between the techniques. Participants explained that this is because the local user's camera remained largely still, which gave little differences in experiencing each view sharing techniques. We also counted how often subjects switched between the two local users in instructing them. In scenario 1, 2D video had the highest user switching count while 3D model had the lowest. We observed that subjects often failed to find a specific tan using 2D video because of its small field of view. Some of the participants stated with 2D video and 360 video, they needed a second to realize where and what the local users were performing. There were no significant differences in scenario 2 since the local users clearly had different roles. Next, we analyzed the subjective performance measure by usability, workload, and social presence. 3D model showed the best results in both scenarios for both usability and workload. Subjects stated, despite the additional training needed, 3D model was especially useful. The social presence score was also the highest in 3D model. This is because subjects were able to feel like they were working together with the local users at the same place with little restriction. The results of objective and subjective measure of performance explain subjects' preference toward each technique. Subjects' preference ranking showed that 3D model was the most preferred technique for both scenarios, while 2D video was the least preferred. To summarize, 3D model was time efficient, usable, less demanding, and the most preferred in one-to-many MR collaborations. Finally, we would like to talk about the practicality of the additional features we implemented for 360 and 3D model. While the zoom-in count for 360 video did not show much difference between the two scenarios, for 3D model, the use of video projector mode and freeze feature was lower for scenario 2. Since one local user had a fixed position, the motivation to use the projector decreased. The decreased use of freeze fix feature was also derived from a similar reason. The user performing the assembly procedure standing largely still. A few subjects stated that the freeze feature might be more suitable for complex applications where it is hard to remember all the changes they have made. Finally, let me conclude and summarize the presentation. We presented and evaluated 3 view sharing techniques for one-to-many MR collaborations: 2D video, 360 video, and 3D model. We compared these techniques in 2 collaborative tasks, and the overall results indicated that 3D model was the most preferred technique with the best performance. As for our future work, we envision to further research view sharing techniques with different multimodal interactions, such as different visual cues or freely conversing scenarios. As the experience of local users was neglected in the current study, we would also like to investigate the experience and interaction between co-located local users for each technique. Thank you.